In the heat of Southeast Asia, where humid air clings to metal and fruit ripens by the hour, an entire logistics operation must behave like a pressure chamber, sealed, calibrated, and under constant control. The fruit in question is no ordinary produce. It's heavy, it's armored, and it's chemically unstable. This is the durian, one of the most logistically complex foods in the global trade network, and every year millions of them are moved across borders by truck, ship, and cold chain. Not because they're delicate, but because they're dangerous. Transporting durians is not a matter of tossing crates into the back of a truck. It's a mechanical puzzle involving weight, spikes, gas emissions, and timing. The outer shell, with its rigid spines, acts like a natural weapon, one that bruises nearby fruits on every vibration. The internal chemistry, driven by ethylene gas, creates a time bomb of ripening that, once triggered, spreads like fire through an entire shipment. One overripe durian can compromise a container holding over 2 metric tons. That's why transporting this fruit demands more than speed. It demands engineering. Crates must be cushioned like aerospace parts. Internal supports must isolate each unit, absorbing impact and airflow stress in transit. In fact, the structural approach used to transport durians shares striking similarities with the cradle systems used for torpedoes aboard naval submarines. Both rely on fixed contact points, calibrated pressure distribution, and directional ventilation to avoid chain reactions during movement. One protects explosive devices. The other protects fruit that behaves like one. Durian logistics lives in this thin space between agriculture and aeronautics, where airflow matters as much as mileage, and internal pressure must be monitored like cargo temperature. Inside custom trays, aerated separators disperse ethylene, while pressure absorption pads prevent the fruits from colliding during turns, slopes, or sudden braking. Each truck, each crate, becomes part of a larger containment strategy, engineered not to rush the cargo, but to keep it from turning against itself. And that's the invisible story behind the fruit that few people see. Behind every durian on a market shelf lies a calibrated journey. A path of controlled chaos, managed not by chance, but by sensors, structure, and the quiet precision of agricultural engineering. This is not just about fruit, it's about how we design systems capable of transporting biochemical time bombs, safely, efficiently, and on a massive scale. Inside a sealed container, the danger begins with silence. Durians, once loaded, continue their metabolic cycle. They breathe, release heat, and emit ethylene gas, a natural compound that accelerates ripening. But unlike other fruits, the durian does it with intensity. When stacked in bulk, in humid environments with minimal ventilation, this gas accumulates quickly, and what begins as a controlled ripening process transforms into a cascading chemical event. A single overripe fruit, under the right conditions, can raise ethylene concentration enough to affect its neighbors. In less than 48 hours, entire batches can collapse under the weight of their own accelerated biology. This isn't a theoretical risk. It's a recurring threat. For years, producers struggled with unexplained losses in transit. Even when temperature controls were applied, the missing variable was invisible: airflow quality and gas dispersion. Ethylene, when trapped, doesn't just speed up decay, it synchronizes it. It forces fruits to ripen together, regardless of destination or shelf life planning. In this scenario, time becomes the enemy, and ventilation becomes the only line of defense. The solution arrived not through trial, but through sensor-driven design. Smart crates, built with embedded ethylene detectors and microventilation channels, began to rewire the way durians are moved. These crates respond in real time to internal gas concentration, opening or redirecting airflow depending on saturation. The plastic walls are no longer passive. They are engineered membranes, constantly adjusting to reduce chemical buildup. The difference is measurable. In controlled trials, identical shipments were divided between sealed crates and ventilated systems. At equal external temperatures, the sealed containers reached critical ethylene levels 36% faster. Spoilage rates followed the same trend. Higher concentration meant higher loss. But with smart crates, the chain reaction was interrupted. Ripening became staggered. Decay zones shrank. The entire cargo began to behave like an orchestrated system, not a chaotic mass. One logistics cooperative in Malaysia implemented this technology along the high-traffic route to Singapore. With modular bins designed for microventilation, they reduced spoilage from 22% to just 8%. That's not just a technical gain. That's reclaimed income, restored efficiency, and hundreds of tons saved every season. The crates didn't move faster. They breathed better, and that breathing kept the cargo alive. Because in the world of tropical fruit logistics, durability is not enough. What matters is biological stability. And durians, unlike other crops, demand intelligence to be moved correctly. They respond not just to distance or heat, but to themselves. In sealed environments, they become chemical saboteurs. Each fruit provokes the next. Each one amplifies the effect. And if the logistics don't account for that reaction, the system collapses from within. Durians don't wait, they ignite. And the only way to contain them is with engineering smarter than the fruit. The durian is not an easy passenger. Its form is irregular, its surface hostile, and its internal mass unforgiving under pressure. When loaded in volume, each fruit becomes a potential threat to the others. A spiked sphere pressing against its neighbors, waiting for the first break, the first curve, the first uncalculated vibration. In traditional logistics setups, this problem has long gone underestimated. Flatbed stacking, often seen as space-efficient, turns catastrophic in motion. When trucks shift suddenly, durians collide. Spines puncture soft points. Microfractures open pathways for rot. In some cases, transit damage accounts for up to 15% of total losses. And yet, the fruit never changed. The strategy did. To solve this, engineers began looking elsewhere. To rail transport, where vibration and weight shifts are constant. The answer emerged in the form of vibration-isolating technologies, already used to transport fragile electronic and mechanical components. Borrowing these principles, designers developed triangular cradle systems. Each durian is seated in an individual cup, molded not only for shape, but for compression mitigation. These cups absorb shocks laterally and vertically, distributing pressure away from the contact points between fruits. What was once a bruising surface becomes a suspension system, and the change is immediate. In Vietnam, this system was introduced along one of its most active fruit corridors, from Dalat, a highland production hub, to the urban markets of Ho Chi Minh. Before the cradle system, damage claims were frequent, and loads had to be underfilled to avoid internal collisions. With the new modular racks in place, damage rates dropped by 67%. The route didn't change. The trucks didn't get faster. What changed was geometry, a new spatial logic that respected the mechanics of motion and the biology of the cargo. Elsewhere, in Thailand, a cooperative sought to scale the idea. Rather than limit capacity for protection, they redesigned the entire bed of their trucks. The result? A double-deck durian rack, equipped with anti-slip surfaces and independent shock buffers. The outcome was remarkable. Not only did they triple the number of fruits per load, but they did so without increasing bruising. Capacity and care became part of the same structure, not competing priorities, but synchronized objectives. Because in agricultural logistics, the road isn't the only variable. Weight shifts matter. Angles matter, and fruit, even when passive, responds to every imperfection in the system, durians especially. Their mass and armor make them intolerant to instability. The solution isn't to slow down, it's to rethink how cargo behaves in motion. Every tray, every rack, every contact point must be intentional, because fruits don't forgive weight shifts. And in logistics, speed alone means nothing if the geometry is wrong. In the design of most transport systems, speed is a central principle. Faster routes, quicker turns, reduced delays. Every efficiency aims to close the gap between origin and destination. But when the cargo is durian, speed no longer holds the same value. With this fruit, haste does not guarantee freshness. In fact, speed without precision only accelerates the risk. The logistics surrounding durian are not about winning a race. They're about managing a delicate biochemical equation that begins the moment the fruit is harvested and continues to evolve, hour by hour in silence. Durian is unique in its resistance to traditional freight assumptions. Unlike apples, which can tolerate longer storage, or bananas, which ripen in controlled chambers, the durian carries its own chain reaction. Its metabolic rate increases with temperature, motion, and concentration of ethylene, a hormone it emits naturally. This gas, while essential to the fruit's ripening, can become its undoing when trapped in confined spaces. Ethylene does not spread evenly, it concentrates. And in the sealed belly of a container truck, the concentration grows exponentially. One overripe fruit sets off a cascade. And no matter how advanced the refrigeration unit or how fast the truck, the damage is already underway if airflow, temperature gradients, and gas dynamics aren't in balance. This is where agricultural logistics enters a new paradigm, one where the cargo itself dictates the rules of movement. It is not the road that defines the operation, but the internal atmosphere of the container. Engineers and producers who deal with durian have come to accept this inversion of control. The journey must be designed not around the shortest possible time, but around the most stable possible environment. Temperature zones must remain consistent. Humidity must be low, but not desiccating. Air must circulate, but not overcool. And the ethylene must be absorbed, neutralized, or diffused at a rate equal to its production. It's less a delivery route and more an engineered biosphere in motion. That's why advanced solutions are now drawing from disciplines outside traditional agriculture. One Taiwanese logistics company, facing high spoilage rates on long-distance durian shipments, adopted a strategy borrowed from high-end flour exportation, a market where sensitivity to ethylene and moisture variation is extreme. Their system combined onboard ethylene scrubbers, atmospheric balance sensors, and active airflow modulation. These trucks do more than cool the cargo. They read it. They respond to it. And by doing so, they transformed the losses of an 800-kilometer route into near-zero spoilage, not through speed, but through balance. It's a form of precision that behaves more like a controlled lab than a freight platform. Modular crate design is another frontier where this logic takes shape. Crates are no longer just plastic boxes. They are engineered microenvironments with airflow geometry, ethylene diffusion membranes, and mechanical buffers that isolate each fruit's kinetic energy. Think of it like transporting a collection of miniature reactors, each capable of triggering the next. What prevents the chain reaction is the containment, the calculated distance, the airflow escape path, the absorption of vibrations during deceleration. When one crate fails, the effects ripple. But when designed correctly, each crate becomes a dam, containing its own risk without affecting the cargo around it. This evolution in design thinking marks a broader shift in how we understand perishable freight. Traditionally, perishable meant urgency. Now, it means complexity. And durian exemplifies that complexity in every stage, from farm to warehouse to customs and beyond. On the field, the fruit must be harvested at peak firmness to prevent internal softening during transit. At the packing site, it must be cooled gradually to avoid thermal shock. At the loading bay, it must be stacked in a pattern that matches the airflow map of the container, not merely what fits. And in motion, it must be tracked in real time, not just for temperature, but for gas buildup, vibration spikes, and even tilt angle, which affects how the weight of the fruit shifts across axles. And yet, for all this engineering, the true insight is not technological, it's conceptual. The realization that agriculture, logistics, and chemistry are not separate domains. They are one system, dynamic, interdependent, and often invisible. Durian forces us to acknowledge that the success of a harvest is not secured at the moment of picking, but at every moment thereafter. And the chain that protects it is only as strong as its weakest crate, its least ventilated corner, its most minor pressure point. So when a durian arrives intact, with its scent contained and its flesh firm, it's not just a fruit on a shelf. It is the result of a precisely managed journey, a collaboration between field workers, transport engineers, materials designers, and atmospheric scientists, all solving the same quiet problem: how to let the fruit arrive without destroying itself. Because in this world of invisible transport, success is not spectacular. It is subtle. A fruit that doesn't ripen too fast. A crate that doesn't vibrate too much. A route that doesn't rush. The triumph lies not in breaking speed records, but in preserving what matters. In a world that increasingly depends on long-distance food systems, Durian teaches us that the future of freight is not about going faster. It's about going wiser. And that wisdom begins by listening to what the cargo itself demands.